pause, that would also distort the outcome of the experiment, which I think you'll appreciate better after I show you a little bit more of the methodology. So I don't think that what they did was particularly unreasonable, as they kept the rats that had learned the task and did it at a high level of performance, up to about 90% efficiency, using a preferred forepaw. However, it's uncomfortable that they were not fully forthcoming in their data reporting. We have a large push in neuroscience to engage in transparent reporting of our research. So a word to the wise: don't do this. When you report data from the experiments you conduct, please be fully transparent in your reporting. Okay, so now that I've shown you the basic structure of the behavioral methodology, and I've stated my critique of their presentation of their experiment, let's actually return to the experiment. The rats were trained on the task until they reached asymptotic performance, which means that the rats that were used in the experiment reached a level of performance that indicates that they had maxed out their ability to actually learn the task. So when this high level of skill was obtained on the 5th day, the brains were extracted from the rats and sectioned in the coronal plane. Bilateral recording electrodes, shown here and here, were placed in the forelimb region of the primary motor cortex, and stimulating electrodes were positioned at inputs to those regions. The electrodes were positioned over the cortex contralateral to the preferred limb, so this is referred to as trained cortex, and over the cortex ipsilateral to the preferred forelimb, so this is designated as untrained cortex. Now they also implanted electrodes over motor cortex representing hind limb function for the contralateral and ipsilateral hind limb. And in addition, they had some paired control sections from animals that did not undergo training. Now next, they administered single pulses of depolarizing current through the stimulating electrodes. Now note that this is not tetanic stimulation, just single test pulses. And they recorded the field potential response of the motor cortex through the associated recording electrode. They found that the field potential response for stimulation of the trained forelimb cortex was greater than the response for stimulation of the untrained cortex. In other words, the synapses that processed motor function in the cortex that represented the preferred limb that was trained to pick up the pellets was potentiated. The strength of these synapses appeared to be greater than the strength of synapses in the motor cortex representing the forelimb that the rats did not use in the reaching and grasping task. And of course, examination of the hind limb cortex and the forelimb cortex of the paired controls revealed no differences between the hemispheres in strength of signaling. So do you see what I mean? They've almost found a needle in a haystack. By doing a rigorous training in a highly skilled task for a rat, they were able to identify a circuit in the brain in which synaptic strength appeared to be increased. Hypothetically, that increase in field strength represents the learning. Okay, but I don't think they were totally convinced yet, and frankly, neither am I. Although I don't believe this is an adequate explanation for their findings, a plausible explanation is simply that the stimulating and recording electrodes just happen to be better aligned in the trained forelimb cortex than they were in the untrained forelimb cortex. Because a very small misalignment of the electrodes could have a significant impact on the magnitude of the response to stimulation. But never fear, Ryu Pedotti was not done yet. The next set of experiments in their science paper, I think, is super cool. In this experiment, another cohort of rats was trained for 5 days in the forelimb reaching and grasping task until they reached that high level of proficiency. And stimulating and recording electrode pairs were placed once again in forelimb motor cortex for contralateral trained cortex and ipsilateral untrained cortex. But now, rather than just recording responses to test pulses, they induced LTP in the motor cortex. In the top graph, you can see what happened when they applied tetanic stimulation in the trained cortex. Tetanic stimulation right here. The stimulation did not produce LTP in this rat. Then they even did it a second time, and it still did not produce potentiation. Okay, let's look at the lower graph for just a minute and see what happened when they applied tetanic stimulation to the untrained cortex. The first stimulation, right here, using the exact same stimulation parameters as they used in the trained cortex, produced a nice LTP. And the second stimulation, here, produced a slight enhancement of the LTP. However, a third stimulation and a fourth tetanic stimulation did not enhance the LTP any further. It seemed that after the first 2 rounds of tetanic stimulation, the synapses were fundamentally saturated and could not be potentiated any further. So do you see where I'm going with this? It appears that in the trained motor cortex, up here, the synapses were fully potentiated by the training even before the first tetanic stimulation. So they couldn't be potentiated any further. They were saturated by the training. In contrast, the untrained cortex responded to 2 rounds of tetanic stimulation, and it was only after 2 rounds of stimulation that the synapses were maxed out. Now, let's look at the upper graph for the trained cortex again and follow through with some of the manipulations that I didn't finish on that graph. So the first 2 times they stimulated and they got no potentiation. So the third time they didn't provide tetanic stimulation. Rather, they applied weak, low-frequency stimulation. And the cortical responses showed a nice LTD. Now, this reveals that the synapses were capable of plasticity. They just weren't capable of potentiation. The failure to induce potentiation was then not because of any misalignment of the electrodes, because they responded with the LTD induction. So everything seems to be working, but the synapses couldn't be potentiated. Excuse me. So next, excuse me. So next they renormalized the baseline, meaning they took this baseline and then just kind of set it at the 100% baseline mark, just to line up everything again. And then they applied tetanic stimulation. Now the synapses actually potentiated. In other words, the synaptic strength in the trained motor cortex was initially saturated. The synapses were maximally potentiated. And then application of weak low-frequency stimulation lowered the synaptic strength, so a subsequent round of tetanic stimulation could potentiate it again. Not only had Ruo Padodi found a needle in a haystack and made a connection between a learning task and potentiation in a specific circuit, but it also seems that they had uncovered an opportunity to explore the range of potentiation that can be expressed in the motor cortex neurons. And we're going to see that in just a minute. I want you to note that the data reported on the graphs on the previous slide represented responding to the electrophysiological manipulations in a single rat cortex. And in fact, it was a fairly rare case in which the behavioral training resulted in a complete saturation or a complete inability to induce any potentiation. So the graphs on this slide represent the means from all the animals. In this case, you can see that tetanic stimulation did produce a small LTP in the trained cortex, where the synaptic strength on average rose to only 114% of the baseline, and the maximum was reached after only 1.18 trains of stimulation on average, meaning that it took only one train of stimulation to reach asymptote in most of the rat cortices, and it took two trains only in a very few, averaging out at 1.18. And actually 3 of the 11 rats tested responded like the rat in the previous slide, where stimulation produced no potentiation whatsoever. And on the other hand, tetanic stimulation of the untrained cortex increased the synaptic strength to 152% of baseline, and it took an average of 2.9 trains of stimulation to get there. This makes it seem like the untrained cortex was much more potentiable. Could it be that the trained cortex had high synaptic strength and the untrained cortex had low synaptic strength? So the trained cortex was near its max already, and the untrained cortex was far below its max for synaptic strength prior to the electrical stimulation. And it would seem that the answer to that question is yes. In their science paper, they reported another experiment in which they gave another cohort of rats 5 days of training. But this time, rather than applying tetanic stimulation, they administered weak low-frequency stimulation. And the results are shown on this slide. I want you to see that the trained cortex could be massively depressed, shown right here. And the untrained cortex, not so much. In fact, the trained cortex, which we hypothesized was potentiated to near its maximum strength by the end of the training, was depressed to 49% of that basal strength using 2.5 rounds of weak low-frequency stimulation on average. In contrast, the untrained cortex could only be reduced to 79% of its basal strength, and it reached this low after only 1.2 rounds of weak low-frequency stimulation. So it looks like the trained cortex was lowered down from on high, and the untrained cortex started low, so could only be moderately impacted by the depotentiation. And this, I think, is an awesome summary and conclusion drawn from the data by Rio Pedati et al. They proposed that a synapse can be modified within a limited set range. In the untrained control cortex on the left, you can see that the synaptic strength, measured by the field potential strength, is moderate in this naive preparation. It can be increased by a few rounds of tetanic stimulation until it reaches a maximum where additional rounds of tetanic stimulation would not increase it any further. Or it can be decreased by a couple of rounds of weak low-frequency stimulation to a minimum, where additional rounds of weak low-frequency stimulation would not suppress it further. But then let's look at what is happening with the trained cortex on the right. The model at the far right suggests that the range of modifiability could go up or down from any set value. So whatever the state of the synapses is at time 1, you could potentiate up a bit or down a bit. Well, this model in my mind doesn't make any sense and certainly is not supported by the data. Because in trained cortex, very little potentiation could be induced and a lot of depression could be induced. You see that the responses to test pulses in the graph fall below the range of potentiability after weak low-frequency stimulation, and they do not reach the heights predicted by the upward shift in the range after tetanic stimulation in this model. So you know what? Let's just cross this model out. And let's look at the other model for the trained hemisphere instead. So this model kind of in the middle here, the model in the middle, shows that the range of modifiability is actually set. It's the same range right here as in the naive synapse, except we're starting out higher up in the range. So it's the same range that was seen in the model at the left for the naive preparation. In this model, we can potentiate a little bit and get to the maximum of the range. Or we can depress a lot and get to the minimum of the range. And so this model does fit with the data. So Rio Pedati proposed that the range of modifiability is set and that we can reach the peak or the nadir. But it's within that range that we will be confined in terms of synaptic modifications. Now, I want to throw another idea out to you. I wonder if this model of range of potentiation might have implications for other learning situations we might consider. So, for example, in the first chapter, I defined learning as an enduring generation or modification of internal representations. And after a little discussion, concluded that the definition of learning should include sensitization to drugs of abuse and the process of addiction. So what if we could identify a set of connections that might be modified by drug exposure, like glutamatergic inputs to nucleus accumbens or inputs to the amygdala? Then expose the animals to the drug treatment or even self-administration of a drug like cocaine, and then see if it alters the magnitude of potentiability and the number of times, the number of trains of stimulation needed to reach maximum strength in comparison with, let's say, vehicle-treated controls. So I'm just thinking out loud here, but I think there could be a whole wealth of stimulating, and yes, pun intended, experiments that could be done by an enterprising young scientist, simply by adding this model to other issues we explore in plasticity in modern neuroscience. Anyway, that brings us to the end of this section of the textbook and the end of this chapter. And I'm just going to wish everybody a wonderful and safe weekend. And I will see you, or, well, not really, but I'll be here next Monday with Chapter 9. Have a good weekend.